Thanks for joining, and it's all yours.
My name is Andrew Ristvey. I'm an extension specialist with the University of Maryland. My area of specialty is commercial horticulture, focusing in on irrigation and nutrient management. And I've got a long story to tell you, so I do want to get going. Do I have the right screen set up here?
Yes, you do.
Okay, good. Let's see. So it's increasing irrigation efficiency in greenhouse and ornamental nursery production with moisture sensors and other technology. Frankly, Chatal, I should have used your title. I thought it was better.
Yeah.
Not that I thought about it. And I read that summary of the that I gave you, and oh my gosh, how many mistakes I've made in the grammar. It was horrible. So excuse everything, and I hope I can make up for it with this talk.
You surely can.
All right. Anyways, so let's move on. So what are my objectives for today? So I want to give you a short history of the research and evolution using sensors and networks to monitor soil and substrate moisture and other environmental parameters in container and greenhouse plant production. I'm going to give you some case studies because I've had a long history since I've been working as a graduate student with my chair of my graduate committee, and now my colleague, Dr. John Leacox, who was a brainchild of a lot of this stuff. And oftentimes I wonder if I'm just riding his coattails, which actually is not such a bad thing because he's got quite coattails to ride on. I will talk to you also about the practical side of adopting sensor networks for irrigation management. I'll talk about substrates, irrigation management, basically your irrigation system and managing that system. I will talk about sensor placement and the things that you probably should be concerned about or things that you should think about if ever wanting to adopt a system like this. And we'll talk about the use of other environmental sensors that help out with irrigation management and just plant production in general. I think that I've made this comment before with a lot of people, growers, extension people. John and I both agree that irrigation management is an art. And it's an art form, but in order to get really good at that art, you need to know some science behind it. And when irrigation managers are deciding how to schedule the irrigation, a lot of things they're integrating. The whole point is to deliver irrigation water for a certain amount of volume at a certain duration. And certainly the irrigation manager has to think of the plant and the basic idea that the plant uses so much water per day. And this is going to vary based on the size of the plant and the different species that we're growing. The irrigation manager has to consider things like the temperature, the relative humidity of the day, the light that the plants are getting. Certainly season comes into that. They have to really consider their irrigation efficiency, their system, and its uniformity, which I'll speak to later on in the program. They have to consider container size. They have to consider their substrate's physical properties and the porosity of that substrate, all to give precision scheduling so that you manage water more efficiently. Because if you over-irrigate, typically that's going to lead to nutrient and pathogen management issues. Because leaching is going to pull your nutrients out of your pot, and you're going to get surface runoff and water pollution. So my colleague, who I used to work with before he retired, taught John Leacox and I a very important factor, or a very important statement, and that was that nutrient management is irrigation management. And so we really have to focus on irrigation. There's all kinds of different irrigations systems. Certainly, you can be very efficient with just using a hand watering wand if your staff is just properly trained. And one grower told me that person who holds the wand controls the profits. And that's something I truly believe in. There's, of course, the easiest to maintain overhead irrigation. It's the least amount of labor. And when you get into drip irrigation, there's a lot of labor involved. But it's certainly the least efficient. And it can lead to a lot of problems if your irrigation system isn't really properly working. There's boom systems. There's really large boom systems. They're relatively easy to maintain. There's very little labor involved, but it really only works with small canopy plants, like starters. You can build your own boom system if you're a mechanical whiz, like one of my growers. He uses boom systems for his annuals. There's, of course, micro irrigation. It's the most efficient if used properly. It can become very difficult to maintain, so it does increase labor time. There's always issues with critters. They like chewing through hoses. Algae builds up, bacteria, particulate, both dissolved and suspended, can clog emitters up very quickly. So there's a lot of maintenance involved with drip irrigation, even though it's the most efficient way to get water to your plants. There's drip lines, which are substrate dependent for even watering. Of course, what we have here is snapdragons that are being grown in a perlite system, and it seems to do well for the grower that's doing this. We've got large mums, fall mums production during the summertime. They lay irrigation line over top of the pots. Their only problem is when either the emitters clog or the lines stretch when it gets really hot and the emitter actually crawls outside of the pot or stretches outside of the pot. There's all kinds of irrigations. You've got misters, which you've got to really try to avoid those misters that are dripping. You got to make sure they're spaced evenly to get even moisture across all of the plants that you're growing. There's capillary mats. Problem with those is that films can develop on the surface. The top dressed controlled or release fertilizers sometimes, if they're top dressed, they're not going to effectively release because that's not where the water is coming from. They may not effectively leach down through the profile, but they're still releasing because of temperature. So you might get a salty top on your plants. And of course you got ebb and flow. It's very substrate dependent. With these, so filtering and sanitation is vital for these sorts of irrigation systems. So you've got all kinds of irrigation systems. One of the things that I think that we'll all agree on is we're really good at knowing when to turn the water on. We're not so much good at knowing when to turn the water off. And that's where these sensors help us out, because they can tell us a lot more information about what's going on inside that container, so that we can reduce the loss of water through our containers and basically the waste of water. Okay, so when we talk about sensors, and I think Dr. Leacox, my colleague John, he really pushes this idea of the process and the symptom of the system. We've got a lot of data in our life. We've got numbers coming at us from everywhere. And if we're going to add these systems, it just fills our lives with more data. And we need a process of filtering that data out and getting information from that data. And that's basically the software that we use. So that data is transformed into information that can be used for knowledge. And from that knowledge, which of course the analyst is going to learn from, we make decisions, and action is taken. And it really is, and each one of these steps, there's this feedback of intelligence. Okay, but what's really important is this step between information and knowledge, so that we can make the appropriate actions with our irrigation decisions, and for many of the other decisions that we have in crop production. So a long time ago, actually it was only about 25 years ago, it's when I started my doctoral dissertation, and it was on primarily nutrient and phosphorus dynamics in container production. Now, what was going on in 1998 in Maryland was that the legislature had just passed the Water Quality Initiative Act, WICWA is what we call it, and it made nutrient management planning mandatory for all sectors in agriculture, and so we had previous planning for agronomic crops, row crops like corn, soybean, and such. But we did not have a process for a greenhouse and nurseries. And so John Leacox was hired a few years before this in order to start developing this process for a nutrient management plan. And it turned out to be more of a risk assessment process than anything. And it's actually a very interesting process. And maybe one day Chantal will invite me back and I can talk to you about the nutrient management plan process and risk assessment for nurseries and greenhouses. But one of the things that John started thinking about was how to manage that water, because as our colleague David Ross had mentioned, water or nutrient management is irrigation management. And one of the things that John was really looking at, that holy grail of plant production, was plant-driven irrigation. Meaning, instead of the time clock, instead of the irrigation manager thinking, well, this is the best time to turn it on and best time to turn it off, let's get some real information about what's going on inside the root zone, and let that information guide us for irrigation decisions. So what we wanted to do was we wanted to identify a sensor technology that would actually work with soilless substrates, because what we had at the time, tensiometers, gypsum blocks, would not work with soilless substrates, primarily because it's a completely different physical nature. Way too porous, way too air-filled, just not the right system for these types of instrumentation. But time domain reflectometry seemed to fit the bill. And what we wanted to do was determine its reliability for various substrates. We had another graduate student who did calibrations with TDR, and we utilized that information on the last year of my project. And we implemented real-time irrigation monitoring and control, and it actually worked. And this is the last year I was growing azaleas and hollies, and this is the azalea data. Note on the to the left of the table, I had 4 treatments. I had cyclic irrigation drip and cyclic irrigation overhead, and that was basically timed irrigation twice during the day to get the containers up to volumetric water content. Then we had the TDR, the time domain reflectometry drip and overhead, which was basically controlled by the amount of water in the substrate. And after the calibrations that we did, we knew where the holding capacity was. We knew where the TDR, the signal, the information that we were getting from the TDR, where that was, and we could develop set points based on that information, and those set points would turn irrigation on and off. And so we could see with the total amount of irrigation we used that we did much better with time domain reflectometry. We had almost half as much irrigation applied, and about a third as much less runoff. Note that the total runoff and leaching, that also includes rainfall. So that's why some of the numbers are higher than what was actually applied. And this is liters per plant during that growing season. But we had problems with TDR. When it worked well. When it did not, it was very complicated to try to solve those problems. Specifically, as far as commercialization, TDR would have never hit the commercial zone. It was far too expensive to utilize TDR. Programming was a bear. You had to be a Campbell scientific programmer in order to program the base stations in order to run the TDR. I couldn't do it. We were utilizing someone who was in communication with Campbell programmers. So programming was way out there. it's not that you couldn't develop the software or the firmware for it, but for what we were doing, it was just out of line. Another problem we had with time domain reflectometry was that salt load, the nutrients, the salts in the container would disrupt the signal and give us false readings. On top of that, we had hardware problems. The TDR probes were connected to cable, and the cables were connected to multiplexers using these connectors. Do you see the pins in those connectors? When those pins drop down below that one level part, you can see the connector to the right. Its pin is lower than the other one. You lose connection with the multiplexer, and then you would get erroneous data, and that erroneous data would leave the system on. So I would come back one morning after leaving that evening from the research site, and one of my irrigation systems was on all night. And so it created problems. And so that was really difficult to manage. But at least at this stage, we knew that the proof of concept was tested, and TDR did work, at least for what we needed it to do. But we had to move on to something different. A few years later, soon after I got my position here at Maryland Extension, we started working with Carnegie Mellon Robotics Institute, and they had a data logger a network system, data loggers that would work with a variety of different instruments. The networks would communicate with each other, and we could utilize this system in place of the Campbell loggers. And the programming was already done. They had a robotics programmer who programmed all of this stuff in. We then started using the Decagon devices capacitance probes, and you can see there's 4 of them lying on that pot to the picture to the right. Those were one of the first capacitance probes we started using. And I liked them. They stretched the length of the pot. They had a limited zone of influence with the capacitance signal, but for what I was using them for in those 1-gallon containers, they worked well. I'm going to show you a video of the process. Now, what it is that I've got those 4 sensors, and they're taking volumetric water content readings. And the system is averaging those readings, and what we're looking at is turning irrigation on at a set point when the volumetric water content went below where I wanted it to, and they would turn the irrigation on. They would then turn the irrigation off when the volumetric water content got to just before it got to container capacity, so it wouldn't leach. We had figured all this stuff out before we started this program. So here's the video. Let me turn it on here. There we go. I think there's some, oh, hold on, wait a minute. There's some sound involved here. I want to turn this sound off. There we go. Let me start this video back up again. Now, it's really grainy because this was 2006 video technology, but you can see, just barely see, the every few seconds, you have a spray of irrigation from those micro sprayers. Okay, now what's going on is we developed a pulse system where the sensors would take a reading, and the irrigation would pulse, for a second or two, and the system would pulse again until the volumetric water content got to be where it was. I stuck those sensors. I pulled the sensors out to get the irrigation going. I put them back in to turn the irrigation off, because by that time the irrigation, the water content was already at where I needed it to be at the offset point. And at this stage, the irrigation, when I put those sensors back in the pots, and they read the volumetric water content in those pots, the system turned off. So we had a system that at least was showing exactly where we wanted to go with this, okay? But the problem is we had some telemetry issues, which we needed to work on. Soon after this video was taken, John Leacox got a Specialty Crops Research Initiative grant. It was a multidisciplinary grant, multi-institutional. We worked with a lot of different institutions on this project, and its main goal was to provide growers with the ability to precisely monitor and control applications of water and nutrients to plants in these production settings based on daily plant requirements, plant-driven irrigation. And so we had this 4-year project, and you can read all about it at smartfarms.net. That's the website. That website's still up, and you can learn a little more about this project. What we were able to do, and pretty much a lot of the cooperators in this had manuscripts, had research that was published in a special series of Hort Technology, December 13. That was, I think, volume 23. So if you go to horttech.ashspublications.org, this is all available. And there's a series of publications based on this research that we did for this SCRI grant. And I'm going to talk to you about a few of those as case studies. One of the really interesting ones that was initially was one of our first kind of projects was to gauge the interest and understanding of these wireless sensor networks to the general nursery community. So in 2012, we found out that the perceptions were overwhelmingly positive about a system like this. There are, of course, concerns of cost and reliability. Cost was one of those things where they were relatively expensive. I think one system cost maybe around $1,500. But the thing is that what we learned, and what you'll read in several of these publications, these manuscripts in this journal, was that the cost was outweighed by the benefits, and even a return on investment. There were so many things that were so positive that it was actually worth the price that we had expected for these systems. Reliability, of course, that was another issue, but making a robust system was important. So the development of robust and inexpensive systems was critical. But we thought that the cost certainly outweighed the expense, or should I say, the benefits outweighed the cost of these systems. Larger growers were likely to be confident in the hardware, but not necessarily trusting the equipment to make decisions. And I can understand that. I will make the decisions so long as we can just monitor and get the information, and that's part of that's part of what we do right now when we're promoting these systems, is to start small so that you can get used to the information that they're giving you before you even start letting these systems make decisions for you with irrigation. Growers most likely facing water restrictions were more apt to be positive about these systems, and that makes sense too. Growers that are paying for water, if they're paying for municipal water, or if they're in zones where they've got to pay for water, growers with less water available to them. These were growers who were very interested in systems like these because of the promise of saving them so much water when they were being utilized. This is an interesting. This next story, it was another manuscript in this journal article, was the cost and benefits of implementing a sensor-controlled irrigation in a commercial pot-and-pot container nursery. So John and his graduate student Brooke Belane found a nursery in Tennessee that was willing to install these systems. It was a 200-acre pot-and-pot ornamental trees, 10 to 45 gallons. It was spray stake irrigation. The irrigation manager, the owner, basically did 3 to 6 minute cyclic irrigations, which were about 0.15 to half gallons of irrigation per cycle. The irrigation was limited by production area and time, not by water supply. The water was plentiful, and the pumping of that water was cheap. So it was really about distribution of water and the amount of water it was taking to irrigate these plants. That was this grower's concern and the limitation. The challenge was that John wanted to know if he could take a block of trees and utilize this system to control the irrigation. And the grower was fine with that. So we did a competition between the grower and the set point control of these systems. The grower, we put on a monitoring system, and this was 1 week of data output with the grower. To the left here in this graphic is volumetric water content. And you can see that there's kind of a blue-green highlight down the center of that. That is the set points, max and min, where we would turn water off and on. But we use that to kind of backlay against the grower's irrigation timing. Those are the, as I said, those are the set points we used when we did control. These are irrigation events. So these the lines that you see that are peaking is the sensor output, and there are 3 sensors that you see that are being used, and this is the average of all those sensors, or should I say, these are the data of all those sensors, and they're really pretty much close together. These sensors were very accurate and precise with their measurements, as the sensor variation was relatively low. You can see an irrigation event was a peak. After the irrigation event, you had drainage, so the volumetric water content would go down. And then there was the transpiration, which is a slightly less of a slope past that initial drainage. And then you'd come down to the bottom and another irrigation event. So the grower was making these decisions and we were just monitoring them. The grower that week used just around 2,200 gallons of water on the plants that he was working with. We had certainly we were using a water meter to determine exactly how much water was being used in these systems to compare. Now, if we go on to control monitoring, you can see pretty much the same information, although those red bars are irrigation events. You can see that there's a peak in the sensor data. Oddly enough, one of those sensors was reading a little high. Now, whether that was because the plant itself was small, wasn't pulling water out, was generally high, whether it was a sensor placement issue, we're not sure. But what we would do is we would use those 3 sensors, and we'd average those 3 sensor readings, and from that average, we would set the max and min on and off, okay? So you would see that at least 2 of those sensors were always within that range. And what cumulative water, if you look at the graphic there, cumulative water, unfortunately, the gallons are the water is now on the left-hand side of the graph. I'll put an arrow over to it. Was just under 1,000 gallons that week that we used for the control. Obviously, to say that the grower had no issues with the growth of those plants during that summer. They grew the same. There was no damage. It was basically delivering the water when the plant needed it. This is a graphic of the weekly irrigation volumes that were applied from April to mid-November. The hashed mark is the sensor controlled, and the straight line, or the non-hashed line, is the grower controlled irrigation. This was under dogwood. We were using 2 different species. Dogwood was a low water user, and you could see that the sensor controlled irrigation was much lower than the grower's irrigation, and that was good. What was very interesting, though, that the grower really did have a modestly good control over his irrigation. He knew when to irrigate, and John was really impressed with his irrigation management. It was even better in the red maple, where oftentimes the grower knew exactly when to irrigate, and you could see that he matched a lot of these peaks quite efficiently. Where he didn't gain was during the spring. He was applying a lot more water than those trees were using in the early spring and summertime. In late summer, he was pretty much right on. There were some points, though, that the irrigation system actually applied more than what the grower did. That's important, too. This is really about not necessarily saving water, but applying the appropriate amount of water for plant growth. You know, especially in the fall, you know, those plants are putting on caliper and they need water also. So backing off water just because it's getting cooler doesn't necessarily mean that's a good thing for caliper growth unless you're trying to control caliper growth. So these systems in general showed to save between 40 and 70% of a current BMP's irrigation volumes. That current BMP would be cyclic irrigation timed throughout the day. So these typical networks would save water in 4 ways. It would save water because of the species. The species are pulling water out at different rates. Some species are more efficient at water, others are not. So because we're sensing water in the root ball, in the root zone, the plants are telling the sensor system when to irrigate. And this is the plant-driven irrigation idea. It reduced the cycle durations. Again, less water, less duration applied, so less water was being applied. And sensors are applying water based on environmental conditions. Again, why? Because it's a reflectance of what the plant is doing. All right, the plant's not pulling water when the temperature is low, when vapor pressure deficit is low, or if it's rained. Plants aren't using that water, so there's no sense in irrigating. And of course, seasonally, where most water is conserved in the spring and fall, primarily because of just the misunderstanding of how much water is actually needed by plants during those time periods. All right, so these are the 4 areas where these sensor systems could work very well. What was interesting about the Tennessee pot and pot operation was that the grower didn't save money from irrigation events. The grower, the irrigation water was plentiful, and it was cheap to pump, and it really didn't have anything to do. Even though the added water that the grower was using, it really didn't matter to the bottom line. What was important was the system reduced the time period that each of those blocks was being irrigated. The grower was limited with time. Right? He had to irrigate his plants, and he only had a certain amount of time to irrigate each of the zones. What this system did was opened up more time for him to irrigate, and he increased the size of his nursery because he could irrigate more. And he was able to profit from increasing production. So this was one of those unexpected benefits of the sensor system for that grower. With the same grower, an economist who joined in on this paper, Eric Lichtenberg from University of Maryland, did the mass balance of funds here. The sensor system cost about $15,000. That sensor system that we utilized in the control and monitoring competition between the grower and John's system, with an annual net savings of around $5,000 for pumping and everything like that. And that's small when you're talking about a multi-million-dollar nursery production zone, you know. So the return on investment was 2.7 years. Not so good. But that's because the price of water per 1,000 gallons was 17 cents. All right. However, if your water is more than that, $1, $2, $3 per 1,000 gallons, where you see that, if not more, in areas within the United States that are water restricted, that savings is so much greater. And that's where, economically speaking, these systems can be of great value. So let's talk about the practical side of adopting a sensor system for irrigation management. So let's talk about substrates. And we'll talk about system irrigation efficiency and placement of sensors. So These soilless media that we're using are highly variable. They are not soils in this last picture I showed. They have nothing to do with soils. They're very unlike soils. They're highly variable. They're made of organic materials, some non-organic, but not real soil. Peat moss, pine bark, whole wood, wood fiber they're using now in place of peat moss, perlite, so many different components. And the physical properties are generally very porous. There are mixes which have a tendency, mixes of those components which have a tendency to leach very easily, so you can over irrigate very easily. And they have a different type of, they have different plant water availability than soils do. And in fact, all of these different highly variable soilless mixes all have their own plant available water. And this is a unique challenge for sensor monitoring. So let's talk about plant available water and the difference between that and volumetric water content, which is what these capacitants are measuring. Volumetric water content is the amount of water by volume in the soil or substrate. It's the plant available water is the water held by the soil matrix, which is available for plant uptake. So the total amount of water equals the readily available water, which is water easily extracted, water buffer capacity, which is the water that's less easily extracted, and then the unavailable water. That's water in the substrate that's no longer available for plant uptake, meaning that the plant can't get to it. Now, matrix potential is what we use to measure plant available water. It's a criterion for measuring soil water availability to plants as it constitutes the force which the water is held by the soil matrix. It's measured in units of pressure, pascals, and other units. We use pascals in our research. It's noted as negative pressure because it's suction. Since plants are using transpiration to as a suction to pull water out of the soil or out of the soilless substrates, and we use a unit of kilopascals. Now, to frame what this whole thing is about, consider a cup of water with a straw in it. Okay. Now, if you were to suck water out of that cup, all right, and you're using this straw, and that straw is the top of that straw is only 5 centimeters away from the top of that water. Every 10 centimeters in height, a head pressure kind of is a negative kilopascal, or it takes a kilopascal of suction to lift a water 10 centimeters in height. All right. So 5 centimeters, it would only be a half of a kilopascal. And so 1 psi is 7 kilopascals. So it doesn't really take a whole lot of energy. Now consider sucking a water out of a straw that's 4 meters high. And of course, this college student is probably attempting to suck beer out of that cup. And that person, that frat student has to apply negative 40 kilopascals to get that water up that straw into his mouth, or should I say probably beer more likely. Now, that's how plants have to do that, and that's the suction pressures that they need to apply. And at 40 kilopascals in soils, that's not, you still have available water, and substrates maybe not. So let's talk about the different textures of soils and how plant available works with them. So depending on the substrates or the soil's particle size, all right, you may have different plant water availability. For sand, you've got a very low field capacity, a small amount of plant available water, and not a whole lot of unavailable water, all the way up to clay, where you have very small particles. You've got high water capacity in field capacity. Your plant available water is relatively large, but you also have a lot of unavailable water. We break that available water up into 3 different types of easily available water, water buffering capacity, and progressively unavailable water. Water that's harder and harder for the plant to pull away from the soil or substrate particles. water buffering capacity is where that transition is between progressively unavailable water and easily available water. And when you talk about irrigation set points, that water buffer capacity is just about where you want to have your set point, so that you irrigate at water buffer capacity, and then you bring it up to easily available water, but not over field capacity. At around 1,500 kilopascals in soils is around what we call permanent wilting point. That's the point where the plant can't get any more water out of the soil and it dies. Okay, that permanent wilting point is much different in soilless substrates. We have done similar research looking at plant available water ratios in various substrates. We used a desorption table and replications. And what we found is looking at easily available water, water buffer capacity, and plant and progressively unavailable water based on kilopascals, okay, that the distribution of water by percent in different substrates is very different. So easily available water in each one of these is between 30 and 45% of that of the water. Now, in the progressively unavailable water, you can see a substantial amount of water is actually unavailable to the plants, and that's because of internal porosity of organic substrates. You can see it perlite has an enormous amount of unavailable water because there's a lot of porosity that roots just can't get to, that the water does get into. Peat perlite, which is a typical substrate, has an interesting mix of plant available water, relatively good easily available water, but a large portion of that's unavailable to the plant. This is a desorption curve or a water release curve for several different organic substrates and some materials like green roof substrate, which is aggregated man-made material. At first, over in the left, where you have that first, and of course, you've got volumetric water content by matrix potential. And so that first amount of water is, you've got a gravitational release down to about 2 kilopascals or negative 2 kilopascals, at which point you have container capacity. Then past that, plants will pull that water out, but by the time you get to around 20 kilopascals or just past 20 kilopascals, this water becomes really hard to get at. That's kind of progressively unavailable water, to the point where past 35 negative kilopascals, that water in that container is not available to plants. And we see that with a variety of different substrates. This was done by Matthew Chappell. He was at University of Georgia, but now he's he's at Virginia Tech at one of their research stations. He's the director there. But he did this really interesting work with desorbing a variety of different organic materials, and you can see the differences in these organic materials and the plant available water. What we can't do is utilize matrix potential in soilless substrates. We really don't have the tools. Gypsum blocks, tensiometers, all used for soil, just don't work that well. Recently, Decagon Devices, now Meter, had developed a capacitance sensor that was a matrix potential sensor. That worked a little bit in peat media, but really, again, it's definitely designed for substrates. So in soilless substrates, we still use capacitance sensors using the volumetric water content as a method for managing soil. Now, let's talk about system performance now. The one thing that, if you're going to consider utilizing sensor systems for either monitoring or control, is you really have to get the efficiency of your irrigation system as efficient as possible. We irrigate blocks of rectangles. All our plants are in rectangular blocks using circular patterns. And you see with this, there's a lot of overlap and there's some that's not overlap. So some plants are getting more water than others. This is a problem. You can solve this problem by adding more irrigation systems, more emitters, kind of filling in those points. And when you have low density, you're spreading those plants out even more, your interception efficiency goes down quite a bit. But when it comes to application uniformity, how uniform is your system? This is where, when you think about putting sensors in, and we don't have thousands of sensors to put in every pot. We only have a few sensors. Where do you place them? So having a uniform application, or having good application uniformity in your irrigation system is really important for you as a grower to get the most information out of these systems, because you'll get a lot of variability if you're not sure where your application uniformity lies. So some colleagues of mine at the University of California, Lauren Oakey, Darren Haver, and Bruno Pitton and I, we wrote an article in American Nurseryman, now out of publication, but nonetheless, if you would like, I can send you a copy, about how to determine your how to determine your irrigation efficiency. And you do that doing lower quarter distribution uniformity and Christensen's uniformity coefficient. Both of those are irrigation tests, which you can use to find out how efficient your irrigation system is running. Read that article. I can send it to you if you like. And that's really important, because an efficient irrigation system is vital in general. But if you want to add monitoring to it, you really want to make sure that your system is running at peak efficiency, so you're getting the best information as possible. Let's talk about sensor placement, which follows the idea of having a really efficient irrigation system, especially with application. You can't monitor every pot or every tree in the ground. What are your ultimate goals? These are the things that you want to ask yourself if you're considering going this direction for monitoring and even control. If you're considering that, you start small and you learn the system. Just get a few sensors with a data logger. Find your most problem areas in your production system, the indicator plants that you have, those plants that are more likely to be water stressed. You learn that area, and then you move on to another location. In soil systems, you place sensors in the root zone. This is typically with around 15 to 30 centimeters or 6 to 12 inches from the soil surface. This is a picture of an installation that John Leacox and I did at a nursery, who are really interested in control, and they really want to know how water moves through their system, because they're water limited, and they really want to. And this is on a river birch, which is a water hog. So they put it on a problem plant in an upper region, where they know they have irrigation problems. I have a system set up for a fruit bush, a bush crop that I'm growing. And I want to know if irrigation changes the phytochemical characteristics of the fruit that I'm growing. So I've got this system at 6 inches below the soil surface, and that's where the roots of this relatively shallow shallow-rooted crop grows. And I've got both volumetric moisture content sensors and matrix potential sensors kind of in line with this. And I'm getting some really interesting data. What I learned from this was that that during the spring, when we didn't have a lot of rain, that my moisture content in the soils dropped dramatically, and it took forever with constant irrigation for me to get that soil moisture content back up again. I wouldn't have known that had I not had those sensors in the ground. So I found this very vital to my research. In container systems, you typically put these sensors in the lower third of the container, pretty much where the water is. Those GS1s, those sensors that I was using here, those volumetric water content sensors, their volume of influence is a liter. That's huge. And that liter really, in the way that that's set up, that liter has a relatively large volume, gets a really good picture of the moisture in that container. So right at the lower portion of that container is where we put our sensors. You place in high stress areas. So if you've got container production where you think you got more wind, more light, more transpiration, you want to put your sensors there because those are the plants that are probably the most stressed and you have to irrigate to. Or you put in plants that are very sensitive to moisture deficit. Let's talk about other environmental sensors and their uses, and I'll finish up here. We had a grower that utilized a system similar to this. They're antirrhinum growers, and they grow 365 days a year. They're growing a lot of crop, and their quality is all based on a variety of different things, not only irrigation, not only nutrition, but they're utilizing a variety of environmental measurements, air temperature, relative humidity for vapor pressure deficit, light. They've got photosynthetic active radiation sensors for daily light integral. Another extremely important aspect of their antirrhinum production. They have sensors in their substrate, and they have sensors in their feed tank, which they recirculate. They're constantly measuring electrical conductivity and pH. So they utilize the whole gambit of these sensors, environmental sensors, for their production. John Leacox has been involved with managing disease and works with one of our fruit physiologists and pathologists in strawberry production. And he's been using canopy level microclimate sensors, the temperature, the relative humidity sensors, which will give you vapor pressure deficit, photosynthetic total radiation. So those are light sensors, leaf wetness, dew and ice sensors. Those sensors are, again, capacitance sensors that you leave out and will detect the amount of moisture that lays on them. So freeze warnings. These systems can, along with a weather station, can alert the grower when a freeze is coming, so the grower can get out there and flick irrigation on, or maybe even the irrigation can be controlled from these systems. If you want to learn more about how you should irrigate, things that you can do, this is a good article. John Leacox wrote it in GPN magazine. That's available for you with that website. John Leacox, right before the SCRI project, had developed a water and nutrient management a knowledge center for greenhouse and nursery production industries. And so it gives you information on substrate management, irrigation management tools. So the irrigation management and the management tools gives you more information on irrigation system audits. That was written by David Ross, our colleague, before he retired. So this is a really good primer for irrigation managers and nursery production people. And this is free of charge. It's online. It's waternut.org/Moodle, which is the platform that this system is on. All you need to do is sign on with your email. It helps John track the use for reporting. All right. I want to thank you for paying attention to this, and I'd like to know if I can answer any questions.
Thanks, Andrew. This was indeed a wonderful presentation, and I do have seen the instances where using sensor has saved a lot of water. In fact, we do a lot in the landscape now, right? Utah has a rebate program on changing even the home irrigation controller to smart home irrigation controller, and they provide I think it's $75 rebate. So yes, sensors can conserve a lot of water, and with it, a lot of nutrient and fertilizers. With that, thank you all the attendees. If you have any questions, either you can raise a hand and I can allow you to talk, or you could type your questions in the chat, and Andrew would be more than happy to answer it. For the audiences who would be viewing this recording, we can put up Andrew's email address, and feel free to shoot him an email, and he's an extension specialist like me, so he is more than happy to work with you all or
absolutely
people.
In the chat, Shatal, I had put my email up, so if anyone needs it, they can grab it from there, or you can distribute it with your emailing list. I'm more than happy to help out in any way possible.
Awesome, thank you. And I don't see any questions or hands being raised. We have our panelists, like Katie Wagner is in this project with me. I tried to pull up her as a panelist, but I could not. But anyway, this was a wonderful presentation. We don't see any questions, so thank you all for attending. And with this, we would like to conclude it. Okay, so there is a question now. Cart, hi Cart, nice seeing you. What's a good source to purchase different types of sensors?
Yeah, so that's a good question. There's a lot of sensors out there, and it's and while I'm not someone who likes to particularly promote one sensor product or another, I just have to admit that we primarily use the meter sensors, primarily only because we've been using them a long time. With the SCRI project, we worked with Decagon Devices. We got used to their sensors. They work with the data loggers that we're using right now, which is called AgZoom, and they work flawlessly. They're relatively robust, but there are sensors out there. Ideally, you want to make sure that the sensor that you have as interfaces well with your data loggers, and that's what's most important. And it's possible that the sensors that you buy from the company, they'll have loggers too, and that. So there's a lot of different companies out there that do it. I think it was Watchdog might still be one of them. But anyways, so we use the meter sensors, and originally that was Decagon Devices. And they have got that MP6, which is now, I think it's called a Terrace 21 matrix potential sensor. So if you're working in soils, that's a really ideal sensor. It's very robust. It's a relatively inexpensive for a tensiometer type of a sensor. And it really does give good data, according to John Leacox.
Okay, and with the AgZoom, you can just set it up wirelessly, right? Meaning the data logger will connect to the valves over the wireless, right? You just need something to power on the valves, and that should work.
Yeah. So let me share my screen one more time, and I'll show you. This is actually can you see my screen here?
Yep.
This is actually my aronia. That's the bush, that's the fruiting bush that I'm working with right now. Mm-hmm. And the system. This is data from this past summer. This was always real time. I had it access to my phone. I have it on the computer, and this basically delivers the system. And this is with the AgZoom product. This is an online system. I can send you more information about AgZoom. Right now, it's only being commercialized presently. We're still in some research phase with it. We're working with the Spanish developers on this. We're hoping that within the next year or so, there'll be more of this out there. I know that John Leacox is going to be retiring soon, and he'll probably be working with AgZoom in perpetuity. So if you're interested in this, send me an email, and I can try to hook you up with John. But again, this isn't the only system out there. There are other systems which I personally am unfamiliar with, because I'm kind of working as in this realm of, we went from one system to another, and this is what we've been working with recently, because it seems to be the most robust and has the at this stage the most amount of flexibility to work with different agricultural systems.
Awesome. Thanks, Andrew. So we don't have any questions now. So with that, thanks, Katie, for joining.
That is cool stuff, Katie. I agree.
Thanks. I hope to learn more about sensors and how to integrate, and like this AgZoom. The one that I have been using is the the sensors would be connected to a data logger via wires, and then the valves would be connected to data loggers with the wires, and there will be a lot of wires. So if there's any way to do some of those wirelessly, that would be so much
Yeah,
fun.
so with the systems that we've used in the past and what we're using right now, we were able to utilize a very low voltage system with a solar panel and a battery that will actually, so you don't have to run copper from one place of the nursery to the other. This is very remote. With the 12 volts, you can turn a latching solenoid on and off. You don't need copper running from one place to another. This can be very remote. So you could have a system with a data logger near the solenoids next to your plants, and that's what we're doing with that one nursery with the river birch, where we're sensing river birch in the top end of his plots where his controllers are, and we have attached a flow meter and a latching solenoid to control that, and it's merely by a solar panel and a 12-volt battery, a very small, almost smaller than a motorcycle battery that we put in in kind of an otter box and a weatherproof box and it seems to be working quite well.
Awesome. Thanks so much. It's already 3:02. So yep, this all will be online for our friends who didn't had a chance to join us today. But thank you so much, Andrew. We hope to bring you sometimes here and talk more about it.
Absolutely, Shatal. It was wonderful seeing you again. It's been too long.
Thank you, everyone.